this snowy day. My name is Jill Dupre. I'm the Associate Director of the Atlas Institute, although today my primary purpose is timekeeper. So I'll be the one cutting off a really interesting talk to make sure that we get to some of your questions at the end.
Well, she'll be negotiating.
I'll be trying. I'll be trying. Atlas is an institute for radical creativity and invention. And when I look around the room, I see some of the faces, including John Bennett, who was the previous director of Atlas, and really this whole front section, people who bought into and supported this vision for interdisciplinary teaching and research. And so thank you all so much for being here. And I'm really grateful to be part of this community of polymaths. And I think we'll be hearing that word a lot in this talk. And I'm going to turn things over to our favorite polymath, our director, Mark Gross, to introduce our guest.
Good evening, good afternoon. I'm not going to bother to read you Alan's bio because it's really long and you can look it up yourself. In fact, I think you probably have. But Alan's Wikipedia page starts out, Alan Kay is an American computer scientist. And I think a lot of people read that and decided not to come to this talk. But there's much, much more. There's much, much more than that. So it's a small part of the story. Today's theme is polymaths. And the poster child for that, of course, is Leonardo da Vinci. He was a painter, for sure, but also an anatomist, a military engineer, an aeronautical engineer, chemist, and many other things. In those days, you mixed your own pigments, so chemistry was kind of an important part of art. Or Hedy Lamarr, to go back into the most recent century, who was a film actress, but also an inventor and engineer, and worked with frequency skipping signal processing. And by the way, her collaborator on that military work was a music composer. So that's the theme of polymaths. I like to think about technology visionaries and virtuosos as people who have the vision and also the technical chops to realize it. So the two go hand in hand. It's really hard to have a strong vision if you don't understand in a deep way what you can do. And it's uninteresting to be able to just do stuff technically without having a vision for it. Now, technology isn't just that computer brick you have in your pocket, your Android phone or your iPhone. It's much, much more, coding in Python. But I think Alan's going to elaborate on that, so I won't. My idea for Atlas, and I've been doing this now almost 6 years, is basically to attract and sustain polymath technology visionaries and virtuosos. So, of course, places come to mind like Bell Labs, or the Bauhaus, or Xerox PARC, which you'll be hearing some about. Now, you expect that kind of thing out of MIT, or Stanford, or Berkeley. I expect it out of CU Boulder. And Alan Kay, who graduated from here in molecular biology and mathematics, is the case in point. He's living proof that it can happen here. I like to think if Atlas existed, back when Alan was an undergraduate student here, he'd be part of this community. In fact, I'm pretty sure of that. So as Jill mentioned, I'm the current Atlas Institute director. I didn't take the job because I loved university administration or management. Not my favorite thing to do. I took it to give others the opportunity that others have given me to pursue their vision. So Alan Kay is one of those people. At age 23 or 24, I was part of the MIT Logo Group, and Alan hired us all to become part of Atari Cambridge Research Labs to investigate and explore computing environments for children. So that was back in the 1980s. It's my honor and privilege and great pleasure to introduce Alan Kay and welcome him back to CU Boulder and to the Atlas Institute.
Thank you. Thank you. Well, of course, the best part of the way this visit started out was to be able to take that ride over the last hill, and there is Shangri-La nestled up against the foothills. And I was so afraid that it was going to be so built out, but it wasn't built out. It really looked so much like it looked 55, 6, whatever it was. And I looked at the campus using the satellite feature of Google, and wow, nobody put a building in the Norland Library quad there. the old campus was pretty much preserved the way it was. Mary Rippon Theater put in a real amphitheater. It used to be just terraced grass back when I was here. So it's been great to visit, and we can blame Mark for this title. And he was interested in this community, which I think everybody has heard of. The exploits of this community have affected everybody, but they've also been worked on by many journalists and many games of telephone. So, and I'm not going to tell the history of this, but I thought it'd be interesting to take the theme of polymaths and take a look at how it affected some of the technological inventions, especially the ones that involved human beings. And any talk that involves science, I always try and find a Sidney Harris cartoon. This is my favorite, I'll confess. But then I realized this reminded me of something. In fact, it reminded me of an advanced calculus class that my old friend Dave Filker here and I took, which we'll never forget, will we, David? Maybe the best class I ever had, certainly the best math class. And so my translation of this is, here's Dave at the blackboard with Professor McKelvey, and this guy was really a friendly professor. The way he taught advanced calculus is he made the students just prove every theorem. So we didn't memorize proofs, we just had a slim book that had the theorems in there, and he would help each and every one of us at the board prove it the way we thought. So we had, if you had an idea, this guy was a good enough mathematician, he could see if you were going to be on a track, and he would, instead of showing us the standard proof, he would help us with the proof that we were trying to develop. It was one of the greatest experiences I've ever had. And the cool part of the story is that this guy was a physicist. He only came over to the math department every 7th year on a sabbatical because his hobby was math. And he just was really one of the greatest teachers we've ever had. But then I found a great Sidney Harris cartoon about, and I'll pause so you can read this group of polymaths here at a table. Tennyson still bidding crouch, whom the rest bade ask. But obviously that doesn't consider an electrical dipole in a spherical molecule. You can see it in Gershwin, Cole Porter, in the Restoration poets. It all comes back to Leviticus. And over here, she says in French, very amusing, but Socrates and his, let's see, allegar edi ora apiena. I used to know what that meant. Allegar is like, but still already, it's now the case that. So it's you find it everywhere in classical Greek. Edi means already or now. Ora is where we get the word hour from. So that's time. So, but it's already time, or it's now time. Apiena. What the hell is Apiena? So I realized I just flunked my polymath merit badge. My old linguistics professor, Mrs. Kashubi, would kill me right now. So I had to look it up. Apiena means sleep. And so the translation here is, but now it's already time to sleep. And I realized, oh yeah, this is the end of the apology. And what Socrates is alluding to is it's time to take the hemlock. But then I realized, oh, Harris is being very funny here, because what she's saying is she's completely bored stiff. There, it's now time to sleep, or it's maybe now time to take the hemlock. This meeting is so boring. And the other thing is it doesn't show them as being really tired, because the big deal about polymathism is it really doesn't count unless you're enough above threshold to be accepted by a professional as a colleague. You don't have to be great, but you have to be above threshold, or else it's just dicking around. You know, it's just not. And so all the polymaths I know who are keeping all of this stuff up are actually kind of exhausted most of the time. And I came to Colorado in '63 after the Air Force, and here's this advanced calculus. Wasn't it Woods that we had? I don't know. Do you remember?
No. What's that?
Our advanced calculus book, wasn't it? I think it was Woods.
I don't remember that.
Yeah. David. But I was also a biology major, and I had a minor in anthropology with a concentration in linguistics, which I obviously did not hold up very well, and another minor in English. And I had to work my way through school, so I was a half-time programmer at NCAR, back when it was down on 30th Street, not up in the Mesa, programming supercomputers. I actually spent most of my time in the theater, and I believe I met my friend Dave in a pit where he was playing trumpet right behind my ear, and I noticed he was playing in tune. And brass players usually are too lazy to warm up, so they play sharp and everybody else sounds flat. If you've ever wondered why the beginning of things sounds weird. But Dave was playing in tune. I knew he had warmed up. So he and I became fast friends. And then I think we found we were both math majors. And I had been a professional jazz musician, still played occasional gigs. And had a lot of fun over in Mackey playing the organs, the classical music stuff. And I also did a fair amount of painting while I was here. So this is kind of my polymath credentials. And maybe too many. And at the end of it, when I got my degrees and stuff, I was so exhausted. I couldn't stand the idea of going to graduate school, neither of those. I didn't want a job. That was the last thing I wanted. And so I was very, very depressed. And but then I realized that, like most programmers, I really didn't understand anything about computing. I was just a good programmer. And they were just really two completely different things. And I thought, boy, if I could get into a master's program for a year, I could avoid graduate school in these other two things. I could avoid getting a real job. And I loved Boulder. And so I looked in Norland Library for all the places that had a computer degree, and this is 1966, that were above 4,000 feet in altitude. And if Boulder had one, I would still be here. And but it turned out the University of Utah did have one, and it was the only one. And if you've ever been to Salt Lake, it's like here, except reversed. The sun comes up over the hills rather than setting and so forth. And so going there was maybe the luckiest thing I ever did. I knew nothing about what was going on. I was just trying to avoid. And to the polymath thing, the interesting thing about all of these successes is in what happened thereafter, I used them all. Every single one of them. And I think, at least to me, an important point is the more things you know, the more possibilities you have for seeing something and seeing connections. So it's really worth trying to get as many facets as possible. So I showed up at University of Utah. And before I got a desk, I had to learn about Sketchpad. And I'm going to show you a couple of these old things, because to me I think the point of this talk is not what we did at Park so much, but why we came to do it. We came to do it because of the culture that was already in existence there, that had started in the early 60s. And so this is on a machine approximately 8 or 9 times the size of this room, at least. And it had its own roof. It was the building that it was in, with one guy on it from 3 o'clock in the morning to 6 o'clock in the morning. The person who had invented this machine, which was a Sage air defense test machine, liked Ivan Sutherland and gave him time on this incredibly huge supercomputer, and here's what he did. So here's the console. And he's going to reach up with, he has a light pen in his hand. The light pen can see what's on the display. And he actually invented this rubber band technique. This is the first time it was ever done. So what you're seeing here is the first real computer graphics system ever done by this graduate student, Ivan Sutherland. Now he just pointed at the edges and said, I want everybody to be mutually perpendicular, and the system did it for him. And you notice it's the first, he has knobs that will zoom in real time. Here he's going to make some dotted lines. So first he makes some guidelines, points at them and says, become parallel. So it just figured that out for him and did it. And now he's saying, what I'm drawing here, be collinear with the lines underneath. By the way, the display can't even draw lines. So he had to program the display itself. It can only put up dots. So all of the graphics you see here he had to do in his 1 year. So now he made the guidelines invisible, so you see the hole in the flange, zooms it back out. Now he wants to make a rivet. And the reason it's called Sketchpad is you don't have to be very careful, because the system will... So now he's using the cross thing as a guide for this arc. And notice what happens here if he points to all of these guys and says, everybody be mutually perpendicular. You can watch it solve the problem here to make a symmetric rivet. And that's not the only solution. He can distort it in a different way, and when he tells it to solve, it will again do the same thing. It will come up with a symmetric solution. But he wants something that looks more like a real rivet. And I think you understand that the system did not have to be told what a rivet was beforehand, right? You saw him draw it from scratch. So there's a rivet, and it's actually a master drawing of a rivet, so now we can get an instance of that rivet. You can rotate it and scale it. You can see that the system led to better displays. But he wants to stick it in the flange there. And now he's showing that, oh, I can get other rivets. These are all drawn from the master drawing. And then he says, oops, I forgot those cross pieces. That doesn't look like a rivet. I'll go to the master drawing and make the cross pieces transparent. And lo and behold, when we go there, we see that the rivets have all fell. So this is object-oriented programming for the first time, done in real time on the world's first graphics system. Pretty cool? So the whole idea of this demo here, now anything that you make can be a master, and he can get instances of that. And he's drawing on a virtual drawing surface about 1/3 of a mile on a side. So you can put enormous drawings on there, okay? So in looking at this stuff, I discovered, well, Ivan, this guy was a graduate student. This was his thesis. 1 year of work writing in machine code, where he had to invent everything from scratch. Invented modern interactive computer graphics the first time. Everything we do comes from that. The first real use of object-oriented design, masters and instances. The programming of the system you saw was not like the programming you're used to, because Sketchpad was a problem solver. So you told it the results you wanted, and Sketchpad figured out how to do it. So most people would like to program this way. Sketchpad could solve these problems, and it could solve nonlinear problems. Here's a bridge where and it doesn't know about bridges, but if you hook it together like this, put force on it, and have Sketchpad show you the stress and strain on those lines, it's showing you what the steel beams would do, because it's making the assumption, which is true, that steel beams are a bit like springs. And so this system, you could put in an electronic circuit and it would figure out what voltage is. So these automatic dynamic simulations, and all of these characters and everything, these are all drawn in Sketchpad. So this is one of the few computer graphic systems in which every diagram was actually done on the system, and it was the first one. What do you think about that? Be nice to have, right? Yeah, so this was Newton-esque, or at least Galileo-esque. And that same week, I saw a programming language that could do a few of these things. And I also learned that the ARPA community was going to do a network called the ARPANET, which we just celebrated the 50th anniversary of. This was just in the planning stage. And I've been in graduate school for about 3 days. And my reaction, this is a technical term. Get used to it, because I'm going to use it a few more times. Well, I could program a computer. There was nothing about Sketchpad that I was mentally prepared for. It was almost the only computer graphics around. I'd never seen any of these things before, and it was like, wait a minute, did I just fall into some alternate universe here? And so the combination of all of those things, plus by my bio major, got me to think about a new way of thinking about programming computers, which is in terms of virtual computers networked together like on the ARPANET. And see, here's the cool thing. A computer, a whole computer, can simulate anything that any computer can do. So it's the most powerful thing you can ever have for a component. You can't have anything more powerful. And what that means is that if you allow them to communicate together, you can make every system that can ever be done on a computer, and uniformly made out of recursive organizations of these things. And the whole data goes away, procedures go away. You're dealing with pure behaviors and pure relationships. So that was the first idea I had there. And then a month later, Doug Engelbart showed up and showed us this.
Well, I can say I'd like to go to produce, but I'd like to go to produce, they get big. I'd like to say one branch only, and let me look just that low, and I see it. Oh, I can say I'd like to see one line only. I can see it. But there's another thing I can do. There's a root I said I have here. So here, I'm afraid I'll need a different picture of the view. So here's what I drew with a picture drawing capability here. It's a slight map if I start from work, and here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that, and oh, I see, overdue books and all. Well, there was a statement there with that name on it. Go back. What am I supposed to pick up at the drugstore? I see, very interesting. All right. Market can do things if I want to just say, I'd like to interchange produce and canned materials. Bingo. And they're all numbered rightly if I care.
So there's a lot more. This is extracted from the thing called the Mother of All Demos, which happened in '68, but he was showing most of that. And it involved things we're familiar with today, like hyperlinking, but the first time in an interactive system, and many other parts of it. Engelbart is known generally for being one of the inventors of the mouse. And this allows me to make a point about these people from the past, which is generally people look at the work done in the past as a cruder version of what we have in the present. Like this is a precursor of what we have in the present. And this is to miss the context that these guys were operating in. It actually makes our present more important, because we're here, than it might have been. And Brett Victor, who is kind of the modern Engelbart, had a great comment when Engelbart died. Brett Victor wrote a great obituary, which is worthwhile reading. And Brett said, well, when I read tech writers' interviews with Engelbart, I imagine these writers interviewing George Orwell, asking in-depth, probing questions about his typewriter. The mouse is the equivalent of the typewriter. It's not the most important thing that Orwell did, although people do love his typewriter. You can get online and see pictures of it. And then Brett says there's a shopping list interpretation, which is all the things we have today, these are precursors that Engelbart did. And this is completely far from what the actual case is. In fact, almost everything that Engelbart did, except for the quality of the graphics, which improved over time, was actually a richer past for a cruder present in almost every case. Here's an example of that. So Engelbart himself said, hey, why are people so excited about the mouse? That's just a button on the radio. We invented a whole car. And this is the car is the thing that's hard to understand. The mouse is easy to understand. So this is how journalism works. And what did it mean that they had meetings with this system in front of them? Well, of course they had video conferencing, but was it like the video conferencing we have?
Set up so I see it over like that. That leaves a corner up there, and I say, now computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected. Audio, you can see my work.
Okay, I'm just going to freeze it there. So on this system, no matter what you did, so this is at the operating system level, no matter what you did, any number of people could collaborate, not just by video, but when you got on this thing, your cursor showed up there, and if there were more than 2 people collaborating, your initials would show up on the cursor. So there could be 15 different cursors. You all had access to the stuff, so it was like an open blackboard. So no system today does that. Google Docs only allows 1 cursor at a time. And the collaboration that we have today is restricted to apps like Skype. And there you can't even share the material. You can only look at it. No operating system today, not Mac OS, not Windows, not Linux, not iOS. None of them allow, in this day and age of the internet with high bandwidth, allow automatic conferencing. It's obvious you can do it because there are little isolated cases of it. But in fact, the people who built the systems today so little understood what collaboration actually means that they could not come close to doing it reasonably. Whereas Engelbart showed this more than 50 years ago now, when it was really hard to do. The difference was he knew what should be done. And the people who exist in the world when it's easier to do don't know what should be done. So here's the way they thought about this. This is about augmenting human beings. And the natural way we think about doing it is to give human beings tools. So cave people would have tools. We have tools. We can hit things with a hammer to make things happen. And in doing that, we get feedback, and a little part of our brain starts turning the color yellow here, the hammer yellow. And we might think about causing other things to happen by hammering them, or we might think about using a nuclear weapon as a hammer. We have done that in this country. We might think of using AI as a hammer. People are thinking about that real hard. So the idea here is that tools without anything else going on usually teach us a very impoverished thing. It's like when you fool around with a piano, you're not going to get what 2 centuries of developing keyboard technique you're going to get. You're going to get a chopsticks culture if you're lucky. Because the piano can't really teach you how to play it. It can just teach you a little bit. And the way they looked at it is, wow, the tools are now 1,000,000 times more powerful or more than what cave people did. So when a cave person got pissed off and hit somebody with a rock, other people could jump on him. Nowadays, if somebody gets pissed off, they have an assault weapon and you can't jump on them. Or they might be a head of a government and have something much more powerful than an assault weapon. And the idea is that any tool you have that has power can be used in any direction. And so part of their idea was you must not use this stuff that's vastly beyond what our 100,000-year-old brains can deal with without a lot of education and training. And if you do that, then you can use modern methods, and if you do that, you can use modern ways of representing ideas. So these 5 things made up what these people thought of as a person being augmented. Now think about your use of the iPhone and the PC. Is there anything connected with the iPhone and the PC that is like this? Not even close. It's only the simple-minded idea that we're going to make you a tool for convenience. There's none of this other stuff. Sure, Facebook is convenient, but nobody needs to learn about what a legal drug is by oversupplying people's desire for social coherence. Nobody needs to learn anything about that. It'd be perfectly innocent. So this stuff makes my blood curdle. It is so naive. And what's worse is the Engelbart people thought about it and wrote it up. And so if any computer person chose to look at one of the towering figures of our past, they would have this concept at least thought by somebody else. And then the idea is if you have a group that's collaborating, it's made up of these quintuples of augmented people, and the group itself has this kind of framework. So this is the way they were thinking. This idea, by the way, was developed in 1962 and then built out to this great demo. So another holy shit here. And then at exactly the same time as the mouse was invented, the RAND Corporation invented the first good tablet. And here's what that system looked like.
Where we may start to edit the flow diagram.
So he's scrubbing out the line there.
A flow arrow, then move the connector out of the way so that we may draw a box in its...
It's where dragging came from. Recognized he wanted a box and made him one. Now it's recognizing his printing.
The printing in the box is being used as commentary only in this case. The box is slightly too large.
Modern day window control.
Then draw a flow from the connector to the box.
Recognizes what he wants.
Attach a decision element to the box and draw a flow from it to scan. We then erase the flow arrows attached to the process post new area and move the box to a new position. This allows us to draw a new box. Then chop off its corner.
Okay, so definitely a holy shit. So what's cool about this, today if you got a flowchart app, it would let you draw a flowchart. That's pretty dumb if you think about it, because you flowchart is a representation of a process. Shouldn't you be able to run the flowchart? None of the flowchart systems you buy today will run the flowchart. You're just making an image. You see how it's been working today? The marketing people will not give you anything that wasn't old and familiar. They're just trying to give you the old stuff in a way that's a little more convenient. But on the computer, on Sketchpad, it's not just for making drawings, it's for simulating the things that you're making. Grail is not just for making a flowchart, it's for creating processes. In fact, the entire Grail system is written in itself. Why not, right? It's a flowcharting system. So all of those things got me and my friend Ed Cheadle here to think of building this machine. So this is a very early desktop personal computer, first object-oriented operating system and programming language. This is a self-portrait of it on its own display, so the displays had gotten a little bit nicer. And then the next year, I learned about Marshall McLuhan. I'll just tell you one important insight that McLuhan had, and I'll tell it to you in engineering terms, which he wasn't. He had a terrible time explaining his ideas because he was a literary critic, so he didn't know either psychology or engineering. But here's what he pointed out, and again I'm translating, that hey, guess what? A radio can't receive a message unless it has a model of the carrier of that message in the radio itself. You need that to tune to the station, but you also need to demodulate that carrier. You need to take the carrier out in some way so that the message that's on the carrier is recovered. And what he said was, hey, guess what happens when you learn how to read? What's important about reading is not even what's in the books. What's important about reading is the changes your brain has to make in order to become a reader at all. And that change was the change that is most strongly correlated with what we call civilization today. There has never been something we call a civilization that didn't have reading and writing. And it's that hidden property of what happens to you when you learn something that is submerged below the fact that you're using the thing for content. But while you're using it for content, it is restructuring you. So that is like a holy cow. And also in '68 was one of the first actual working flat screen displays at the University of Illinois there. And I also ran into Seymour Papert. And Papert's idea was there is something very special about the computer that makes what seems to be difficult and abstract in mathematics, that can make it into a concrete and manipulable experience even for young children. Now, I was a mathematician, I was a computer guy. I knew everything that Papert was doing, except I'd never thought of it in terms of children. He was. And in fact, he was a very good mathematician. Many of the things he did allow things like calculus to be taught in a better way than you can do in high school to children who are 9 and 10 years old. And this is maybe the most jaw-dropping experience of the whole thing. And on the plane back from this visit with Papert, I drew this cartoon. And when I got back to Utah, I made this cardboard model. Because I believed what Papert was doing. I realized the flaw in computing was we're thinking of it as tools for adults, like guns. But in fact, Papert was thinking of it much more like a book. I later called this thing a Dynabook. But if it's a book, if it's about literacy, if it's about reading and writing in new ways, then you have to start with children. It gets harder and harder because this is a paradigm shift, a shift in epistemology. And ARPA was working on both the wired network, but it was also starting to do wireless. And of course, it had to be end-user programmable, had a stylus tucked in here. But meanwhile, I had to finish up my thesis. So this idea. So here's my reaction. I'd never had ideas like this until I just happened to walk in at Utah. The context there was so rich, so different, that I just started having ideas in spite of myself. And this is something we should never lose sight of because it's the best. It is really hard having ideas outside of a context. The context provided by ARPA. And these ideas, as I say there, I didn't think they were coming from me. They were just coming. They were just reactions to all these things that ARPA was doing. Well, we mentioned Leonardo. So let's suppose you have twice the IQ of Leonardo, but you're born in 20,000 BC. How far are you going to get? He was actually in the wrong century for what he wanted to do, and no amount of IQ could transcend the century he was in. So he did drawings, but he couldn't make things. Whereas somebody nowhere near the intellect of Leonardo, Henry Ford, did it easily. Ford made millions of self-propelled machines without any large effort because he was born into the right century, a century that was already doing things like this, that already had technologies that allowed Ford to add to it his thoughts. And why was he born into the right century? It's because this guy, Newton, completely changed the way of looking at the world in maybe the largest qualitative jump in history to what was in the Middle Ages and the Renaissance, which Leonardo existed in, to the kinds of thinking done in our modern world. And that happened at a very good time because just about 100 years later, the Industrial Revolution started. And the Industrial Revolution wasn't just about engineering, it was informed by science. And the combination of those things was extremely important and powerful. So point of view is worth 80 IQ points. I think of this as knowledge is silver, but context is gold, and IQ without the other two is basically a lead weight. It's essentially a pop culture thing. IQ without these things is being clever and outwitting other people. But it's the accumulation of these things that makes the big difference. And what I was experiencing at ARPA was that idea. So this could be any curve that you want. You can pick what it is, but suppose it's reading scores in the US. That's a typical yay, boo, yay. For reading, it's completely meaningless. Because most things actually have thresholds, and if most of the children aren't really learning how to read, it doesn't matter whether the reading scores are going up or down. And the biggest flaw people have in thinking about simple data is not to establish the thresholds that constitute meaning. So this is a very important idea for polymaths. What you care about is, are you past that threshold of what is actually needed? And we can see that trying for the top and trying to improve are both enemies of this. You can do a lot of things that makes you feel good down here, and it means nothing. And perfection is hard even for angels to get to. So what you want is a process that finds the first blue area. It's the simplest thing that is qualitatively different from where you are. But once you're there, you're in a different world. You're in a blue world. It has blue thoughts. You can do blue things. And if you're working on difficult things, you have this problem. You have to withstand society. You have to withstand your parents. You have to withstand your teachers. Because what everybody wants is continuous improvement. Americans especially hate learning curves. American marketing really hates learning curves. They won't sell anything that has a learning curve. They wouldn't sell a bike if it were invented yesterday. Too dangerous, all those lawsuits. Too hard to learn. They just wouldn't do it. But often, to get past that barrier, you have to go through quite a bit of learning. The ARPA community was willing to pay for that learning. So they didn't just pay for problem solving. They put probably 40% of their budget into problem finding. And they made the assumption that any problem that can be articulated from the present is probably not the problem you want to work on. You have to find a future or a qualitatively different version of that problem, or you wind up doing something incremental. Now, here's the 1 second explanation of what I've been talking about. ARPA is over here, Xerox PARC is here. Here's the internet. All the stuff flowed from the radar efforts in both UK and the US during World War II, especially Building 20 at MIT. And there was a lot of effort at Bletchley Park. So of course I can't explain this, but I'm trying to give you a sense of why things are difficult. And Thornton Wilder had an old fortune teller in the time of your life say, hey, I tell the future, nothing easier, right? Just whatever you want to say. Hasn't happened yet, but who can tell the past? The past has all this detail in it, and a lot of it is too complicated to make up a simple story. And Goethe pointed out, boy, it's hard to identify heroes without a lot of disclaimers. Because when you have a whole community doing this stuff, the ideas go back and forth. And there are individual heroes. But you have to take what I'm saying here with a grain of salt. This is much, much larger than even a whole university course. So here's Xerox. And so a small number of us got invited there to pursue things we're in. And I had a real yen to see about this children's computer for children of all ages. And these are obvious, but you can't tell from today's technology. So persons are the most important thing, children are the most important things. So if you lose sight of that, you're just making gadgets. And that means there needs to be a course called Persons 101 and Children 101. And here's the crib notes for your midterm exam. So a person is a mixture of Hamlet, 7 plus or minus 2. You know about our cognitive load limitations. System 1 is the animal part of our brain that is like a neural net. It does correlations. We're cultural animals. We can't exist or even learn outside of a culture, and our minds are not unitary. We have at least 20 definable minds inside of us, and some of them are critical to understand. So our minds are like theaters. They're really tiny. 7 plus or minus 2 in most studies recently. That was for memorizing letters and numbers. It's really more like 4 plus or minus 3 before you get overloaded. So the theaters we have are tiny. Why do I say theaters? Because we think in terms of stories. And that can make us feel good, but in fact, stories don't have much of a mapping onto the real world, as people found to their surprise when science finally got invented after 200,000 years of us fooling ourselves with stories. And our minds are mostly animals. Something we don't like to talk about. And if we were born anywhere in the world but taken to, say, Paris, we're going to wind up French. If we're born and taken somewhere else, we're going to wind up wherever we go. We're set up to learn the culture as reality wherever it is. So that's efficient in one way, but it is a true source of problems. And this multiple minding thing, I'm not going to mention 20, but we have a whole mind just for tactile kinesthetic. Like we can touch our fingers behind our back without looking. We know where we are in space. We learn when we do things, when we drag things around, when we touch them. We have a mind that is iconic. It's visual. I can see about 100 things at once. And pictures are about 4 times more memorable than words. And what's fun is if you put 100 words up on a wall and you just draw boxes about them, they're twice as memorable as the words without the boxes. Because the boxes, I make the words into half pictures. And so it engages the picture part of your mind. And the thing that makes us interesting and also dangerous is the extent to which we can use our language facilities for layering ideas on top of things that our genetics was never directly set up for. So we're more theatrical than we assume. We treat our beliefs as reality. Smaller than we assume. We can't take in whole contexts. We're much more non-human than we assume. We hate the idea that we're not human, but we are. We react rather than thinking. We're more culturally shaped than we want. Our conclusions are mostly social. This is the disaster. Most people cannot do something just because it's a good idea. About 85% of humanity won't do something unless they sense their society around them also believes in the idea. So this is a critical problem in our modern day. And we're much more fragmented than we think. We think of ourselves as unitary rather than a bunch of minds, even to the extent that when we see a candy bar and an apple, and we have a conflict on the thing, we don't think of this as being 2 minds, each one wants something, and we only have one body. This happens all the time, and we're quite used to it. So the key here is we can use these things for positive things once we are realized. This is why anthropology is a good idea. I think it's probably the only required course I would put into both K through 12 and college. It's surprising that in a liberal arts university they don't make people understand their own species. Isn't that funny? Yeah, so we're way off. So hang on.
But I drew a picture.
I know. but I'm using words. So when we thought about children, we thought about many more people than this, but here's Montessori pointing out you can't teach the 20th century in a classroom because we're actually set up by nature to learn from our culture. So if you want children to learn in epistemology, you have to make the school into something like an entire environment. And this is Montessori's idea. If you want to learn French, don't go to a classroom to learn it, go to France. Another thing that Seymour said. And one of the big influences here was Jerome Brunner. I'll just mention this, that here's his challenge. If you need to teach intellectually honest forms. If you're teaching them to children, you're going to have to invent new forms that embody the content. Like if you're going to teach children mathematics, you have to figure out the mathematics that their brain can handle, and it has to be real mathematics. So, like, you probably don't want to teach children fractional arithmetic at an early age. It's absolutely a dumb, it doesn't match up well with what they do. And okay, so let's take, so this is going to take about 8 or 9 minutes, so forgive me. So well, in computing, you have to do real things because you can't prove much. So we needed a Dynabook to experiment with, and we couldn't make one because the displays didn't exist. And so we had this genius, Chuck Thacker at Park, who made an interim Dynabook. So this is the day it started working. And you see on the screen there's a Cookie Monster that was drawn on the screen. And in fact, here's what this machine could do. You can see it's a little bit more powerful than a Mac was. This was done 11 years before the Mac. 11 years. And because this was an emulation computer, it could also do 12 polytimbral real-time voices. And you could just hook the keys from any keyboard into the machine, and you had the first real-time synthesizer that was polytimbral. And it was made for children, so we work with hundreds of children there in the same spirit as Seymour Papert. And how did we program this? Well, this idea of little virtual computers on a network. I had another genius, Dan Ingalls, and here's a progression of user interfaces, which will look sort of familiar to you. This was desktop publishing with embedded graphics, and you can see the user interface comes up there. And towards the end of the 70s, we built machines with larger screens. And in fact, I have a revival of one actually running here. So this is the, now I switch over, it's designed to use. So this is actually a running version. Let's see if I can find, here we go. And it was done for this first portable machine. And so it's called a note taker. You notice it has the same recognition thing here. And we're running it on this larger machine right now. And how do we get it? Well, here's, right there is a disk pack of hundreds that Xerox threw away of this work. Rescued, and on it happened to be a file that had the system on it. And this system was in the form of a complete network. So it included everything, including the, it was like an internet where objects were connected together. And because the whole thing was contained. All we had to do was write a little emulator for the machine that it ran on, and the whole system started working. And you're looking at it right now. I'm using it to give you this presentation. And this gives us a time machine taking us back into the past. And the only difference between this system that I'm showing you today and the past is the emulator has much more memory. So I can show many more bitmap pictures than we could back then. And here it is. So this will look, and by the way, this is the system that Steve Jobs saw in his famous visit. So you'll have some interest to see what he saw and what the Mac did and didn't do. So so among other things, well, there's the overlapping windows. In this system, you could use the, for instance, suppose I wanted to center, I can use the recognizer to center it, or so the gesture recognition. Here's a painting I did like 45 years ago, and it's live, so I can select some paint here, I can select a brush here, and I can scribble it up. The recognizer and so forth. And now what am I showing here? Well, this system had unlimited desktops. Each desktop is live. So these are not pages in a presentation manager. Right? Why would anybody want that? Right? Once you give the presentation, you're dead. You cannot interact with the thing. Isn't that crazy? Why did they do that? So here, each one of these things is live and it persists over time. And so I can give a demonstration of anything I want just by sequencing through these different desktops. You can see where I've been here. Here's the slides I just showed here. Here's where I am now. And here I'm going to go look at something, again, would be nice to have. So this is called an active essay. So again, it's a desktop, but this is a 12-year-old girl who wrote this article, which was published in a magazine, but she did an active version here, and you can see what she did. So here's a simulation of the computer that she used. And so making a box called Joe, and I can say, Joe, turn 45, so this is kind of like logo. I can say, Joe, grow 100, right? So I would like to be able to do this today. One of the things that frosts me the most is none of the media systems that you can buy today will allow you to run active content in it. It's all imitations of past media. You can't do this in Microsoft Word. You can't do this on the net. You can't do it in Wikipedia. How crazy it is to go to an article on a programming language in Wikipedia and not being able to try the language. So this is complete blindness. Okay, so I'll wrap up now. And I'll just go past this.
And now.
Okay, so the last idea here is a little something about communication. And Licklider, who set up all of this stuff, wrote this memo in 1963 to the members of the Intergalactic Network. Why did he call it that? Well, they asked him, and he said, well, engineers always give you the minimum. And I want a worldwide network, so I'm asking for an intergalactic one. And he got it. And he had this idea, which was, if we make an enormous network, our biggest problem is going to be learning to communicate with aliens. And he meant that once you get larger than the context you're in, you start losing the commonalities that are needed for communication. So it's like communicating with aliens, and there's this problem of if you have two different contexts, you could be in trouble. You could both be human and a mane and hooves and a tail. This is a joke if you're a medical person. Right? This is called overdiagnosing. It's a zebra! No, it's just a horse. Here's the conflict between candy bars and apples. And then the question we had back then was, what kind of shared context can you put together to allow you to communicate with a computer? And what you're doing is negotiating common areas. And again, theater comes to play here, because think about what theater is. The audience doesn't get to interact with the play. So the playwright and the actors have to supply what would be the negotiation. And in theater, it's called the magic mirror in the profession, because the idea is to beam the audience's intelligence back out at them to get them to think about things they haven't thought about for a long time. And same thing with writing. Writing has to do the negotiation. This is why writing for most people is difficult, because they're like children. Children think everybody knows what's on their mind. And so they just say what's on their mind, and that isn't what writing is about. Okay, so one way to think about it is all of these communication things are kind of like pointing, because we're pointing to the thing we hope is common between us. So to get computers to talk to each other, well, we had to do that with the internet and also with object-oriented languages. And of course, we might have to deal with aliens someday. So for this computers and humans thing, we've got this theater. What should we put on the stage? And our solution was, let's put what the computer is thinking on the stage, but in a form that humans can deal with. So this is where the graphical user interface came from. It is a theater that's explorable. And when you put the pointer into a window and it comes up to the top, you're choosing a context. You're choosing here's what I'm going to talk about next, and the computer knows what you're going to talk about next. So you're moving from topic to topic. You want to have all of the things available. And then these three mentalities here need to be combined. You need to do something with this, because this is not just memory, but dragging is intimacy. You're holding on to something and moving it around. And the reason the Mac, that interface, was popular is because most people who used it felt some sort of rapport with it. There was a bond. That bond comes from the kinesthetic part of things. So this is Jerome Brunner 101. And then the thing that's left out in most interfaces is the fact that there is a new literacy here because you have a computer. And so any interface that doesn't allow you to program safely at any age is very poorly designed. It's basically made for people that the technologists think of as intellectual cripples. Here's a good place to quit. So to do this interface, and you could argue that there's like 8 inventions that needed to be done to get the modern world in computing and networking. The gateway one was the GUI, because without it, you don't get 4 or 5 billion people being able to communicate with the computers. It is the intermediary between them. And here are the disciplines that were needed to do that design. And the way it worked out was there was one person who could do those disciplines and a bunch of people who could do several of them and do them better than the person that could do all of them. Right? So the person who could do all of them could talk with everybody in the team. And like Dan Ingalls there, who was a much better programmer than I was. I let the better programmers do the programming. All right, so you have this combination of differences and similarities that allow you to build extremely powerful teams. And with that, thank you very much for inviting me, and I hope to visit again sometime. Thank you.
Exactly our agreed upon.
Well, and you started 3 minutes late because you and Mark. Come on.
So we have about 20 minutes for questions, and I'd like to give preference to students. So the first question I'll throw out to a student if there's a student question. But you have to do it quick. Okay.
Oh, yeah.
Where do you think the education system is headed in the next few years?
Well, the education, he's asking where do I think the education system is headed in the next few years? And I'm presuming you're talking about K through 12?
More higher ed, actually.
Oh, higher ed, okay. Well, I think the most difficult, because humans are so imbibed with the context that they grew up in, context that they work in, they're not aware that they're in a context. So McLuhan had a great quote. He said, "I don't know who discovered water, but it wasn't a fish." Because our nervous systems are absolutely set up to damp out anything that's constant. It's called accommodation. And McLuhan pointed out the number one thing we need to pay attention to is the stuff that we've damped out. It's the stuff that we had to learn in order to do things without, like we read without difficulty. So we completely miss what happened to us when we learned to read. So, so my reading, I don't know how to criticize higher education in general, but I can certainly do it in particular, in that most people I meet who have college degrees are, you can never get really educated, but there's this threshold idea. And in my opinion, most undergraduates that I've taught in the last 30 years or so, and most people with college degrees that I've met aren't past any threshold that I would call educated. Not even close. Because they don't know the most elementary things about their own species. And it seems like the basic notion of education is it's different than training. It's different than a vocational school. It's about context. It's about perspective. And you can think of 10 or 20 things that we need to have much more perspective on than humans generally do growing up in any particular culture. So I believe that education is flunking that terribly. And it happened, I saw some of it happening because many universities, like my wife went to Stanford, she missed, the year before was the last year they did a Western civilization course at Stanford. And she never, that wasn't part of her Stanford education. There was no context for most of the other stuff she was learning. There are other things that were taught in lieu of Western civilization. But it absolutely doesn't make sense not to try to prioritize the impact of knowledge. And so I think that's worse today. I think the idea that people have that they should follow their own bliss is a really good idea. But if they try to do it without gathering context, they're nuts. Because, when you're 16 years old or 17 years old in high school and you decide you're going to decide what you're going to do for the rest of your life, that is the worst mistake you can ever make. And somebody needs to explain that to the kids. And the reason we have compulsory education is precisely because it took us 200,000 years to discover science. There's nothing obvious about the stuff that's important, and that's why we have schools, K through 12, and we have colleges. It's exactly for the stuff that can't be learned as an apprentice. So yes, sir. Yes, hi.
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 What does your house do with that big pile of junk computers?
The pardon?
Big pile of junk.
Oh, well, that was around here. Oh no, let's see, we're in Boulder. So it was I think between Palo Alto and Mountain View, that Xerox dump there. Yeah, quite a few of that of the work was lost. This revival that I showed you was a Christmas project that a bunch of us old timers did just for fun around, I think, 2014.
Still sitting there?
This thing, I would not be surprised at all. It's probably, you know what PhD means? PhD means piled higher and deeper. And I'm sure that pile is piled higher and deeper now. We were very lucky to get that because it happened to be the only file of this particular system that was ever recovered. And in fact, it required a fair amount of archaeological work to figure out what it was. We had to look at kind of the raw stuff on it and then figure out what was the minimum, what could we do to bring the thing to life. Fortunately, everything it was doing its own screen painting, not using anything else. So there's no extra code in it. And by the way, that whole system, including the operating system and the development system and everything, is about 10,000 lines of code, if you want to compare that with the way programming is done today. Today, that would be probably about 1 million lines of code or 10 million lines of code or so. It's because this is the power of mathematics. If you have a mathematical bent, then you can see that what you're doing with computing is a set of relationships. The problem is math doesn't run well. Math assumes basically infinite speed. But if you can find a compromise between math that won't run on a computer but is very compact and something that's, say, twice the size of that does run, that's what you're seeing there. You wind up with code that is maybe a factor of 1,000 smaller than the way typical programming is done. Yeah, the field has been very incurious as to how we did all this stuff. That is what is, just as they are incurious about Engelbart and incurious about Ivan Sutherland. Because our field is basically a pop culture. And a pop culture is all about an individual saying, I'm here too. And so they're not interested in the past at all. They're interested in what they can do. And they don't care whether it's better or worse than the past. Because that's not what it's about. It's basically proclaiming identity. And if you have that in a field that purports to be an engineering or a scientific field, watch out. Because they will lack the discipline to establish those thresholds that will make the system safe. And also they will lose the ability to retain the quality of some of the better ideas from the past. This is why I show this stuff, because I would just want I rub people's noses in it to see that, yeah, the displays got better looking, but the software got worse. And one of the ways of thinking about it is, if you're going to reinvent something, you better reinvent the wheel. That used to be frowned on, but right now I'd take it any time. Because what's being reinvented is the flat tire. I've got a true believer. Okay, yes?
Do you see any places that are making actual wheels? Right now?
Well, in biology, there's a place called Genelia Labs outside of Washington, D.C., which is pretty darn impressive. That is a very Xerox PARC looking place. I don't know of a computer place. The quality of the people around, there are numerically more people around today of the quality of the PARC and ARPA people. Percentage-wise, it's much worse because of the pop culture aspect. There are millions and millions of people who probably shouldn't be writing code. But that disparity also exists in a smaller way in the in the 60s because the people who worked for IBM were not really that good. And what I'm trying to show was, wow, if you don't have this context of the ARPA thing, none of us were any good. I was surprised at the ideas that I had. And all of us, when Park went away, when we have meetings, we all talk about, wow, we haven't been nearly as productive. We've done things, but the synergy is gone from the thing. So one way of thinking about the bottom line that I tried to sum this up is that the quality of the results is most strongly correlated with the quality of the funders. Because if you think about biology as variation, every generation will have that 1 in a million or 1 in 10 million person. You can guarantee it. The real question is, do those seeds fall on fertile soil or not? And this is where the funders actually take the funders who don't try to control. So the big deal about the ARPA funders was they didn't confuse the responsibility, which they had for all this money, with the need for controlling. You can't control an artist. Right? It's like herding a cat. Can't do it. You can get a cat to do anything you want if you present the cat with a situation that it wants to do. You have to figure out what that is, and that's what a good research manager does. They just set up an environment. Like Licklider got hundreds of people working on the following vision. The destiny of computers are to become interactive intellectual amplifiers for all humans pervasively networked worldwide. That's what he said back in the early 60s, and he never deviated from that. And he didn't know what that meant. He didn't know how the networking was going to be done. He didn't know what an intellectual amplifier was. It didn't matter, because people came out of the woodwork, and Licklider was happy to take 70% not fruitful, which he didn't think of as failure, but just overhead, to get the 30% that would change the world. Right? And if you think about it, it was cheap at the price, because cost, in today's money, it probably cost maybe $500 million to do this. Park was maybe 100 million. And the return has been on the order of about $60 trillion now on this. So the return on investment of trusting the researchers and setting up a good process is far, far more than any business person ever complimented. They only want to make millions and billions safely. And most of the millions and billions they're making are made from these unsafe processes that are no longer being funded. Haven't been funded in this country for like 35 or almost 40 years now. Yes?
So related to that, in your opinion, where do you think could be the equivalent across to the Engelbart back in 1970?
Well, I don't know, because if you think about the Xerox was a fluke, and Taylor had to get Xerox to sign an agreement that they wouldn't mess around with us for 5 years, which they hated, but they did. And the reason is that companies don't get rewarded for doing edge-of-the-art research. There are no tax breaks. There's not even anything like depreciation. Research gets charged as just an expense. And so most companies would rather use capital and do acquisitions after somebody's done it, but they don't realize that their company culture gets diluted every time they acquire. So they eventually wind up with less and less synergy in the company, and they can't do much. So so again, looking at the one example we have that worked really well, the government launders money that it gets through taxes. So it puts an intermediary that companies, it's like you're spending their money, even though you aren't. But they feel like it, and they want you to do what they need rather than what is actually needed to be done. So the government short circuits that, it takes the money away, and it's a redistribution agency. And The other unfortunate thing is this only works in a democratic government when there's an enormous threat, like war. It's completely correlated with that. Why? Because the reasonable people who run things absolutely do not want to deal with people like artists and scientists. Those are the last people that they want to talk to. And it's only, like, same thing in the UK. They were completely against boffins until the threat of Hitler, and then all of a sudden they were able to set up Bletchley Park and do the radar stuff early enough to save the country. But as soon as World War II was over, they threw out Churchill, and they failed to reward the people who actually did the technology that won World War II for them. And business people are that way. They're not there to improve the world. So trying to get this kind of stuff funded in a business, especially in the public domain where it needs to be, because you need to, these large things create industries, not just products. And industries can't be done by any one group. You have to put the stuff out. So this is like the exact opposite of the hunting and gathering instincts that most people have. This is like agriculture. This is like building. And if you think about the US, we are a country that is built on cooperation. But the next level down, every business is competing against themselves, and every human is competing against every other human. So this is nuts. But we are. We are a crazy species because we feel punished when we're taken away from people, but as soon as we get in a group, we start trying to take advantage of it. And so do monkeys, and so do chimpanzees, and so do other primates. This is not a purely, this is why I say we're not nearly as human as we think. Those conflicting impulses are actually something you'll find in most mammals, but especially in primates. Worth pondering. Yes?
So you've been on a bit of foundation, you've worked in the private sector in research, you were in academia. For a polymath who's trying to create an impact, do you think there's a clear path?
Well, so nobody, the number one thing here is nobody who does the kinds of things we're talking about is other than an optimist. And if you think about it, it doesn't make sense to be pessimistic. You're just, might as well be an optimist and just take more shots to the chin. But overall, you'll have more of a chance than if you're pessimistic. You'll dodge too many things. So the number one thing, be optimistic. Compared to this golden age I've been talking about, it really was. There's nothing like it right now. Like the best person I think Brett Victor he's definitely in my top 2 or 3, maybe even of all time, but especially in this day and age. He can hardly get any funding because he's working on a thing that's really a 10-year out thing. It's wonderful. They've built it. You can use it. It's a whole different way of thinking about its computing as part of it will be 15 or 20 years from now. Fantastic. You can't get a dime from all these Silicon Valley billionaires because they're not interested in anything they can't turn into a product. And the government is afraid of being criticized by Congress. So the NSF has always required both peer review and in computing proposals that are akin to engineering proposals, which means you have to explain to them how you're going to do something, and that's not what research is. Research is having an idea about how you might, it's basically about saying, yeah, the conditions are very good for this kind of thing. Give us some money and we'll find out. So that doesn't really exist today very well. Universities could do a much better job. So MIT, for a number of years, it had a fund which was part of its endowment, where they did their own funding of certain professors who couldn't get normal funding in peer review processes. One of the most famous was Norbert Wiener, the cybernetics guy. And the president of MIT just decided, hey, we should set up a position called institute professor, and we'll not only pay their salary, but we'll give them, today it would be like $500,000 a year to do whatever they wanted, put a couple of students on some idea that's too crazy to even talk about. So you have to do, the other way of looking at it is this enlightened funding is like the MacArthur Fellow Grants, but for groups. I've tried to get the MacArthur people to understand that so many important things are actually done by groups of people. And by just restricting to individual artists, they're doing a good thing, but they're missing the point of the whole process of a bunch of arts that they can't recognize. And so far I haven't been able to convince them. I've been on their committees for choosing MacArthur Fellows, but it's basically they have this thing that they do and they're proud of it. And they really don't want to hear about how a lot of things need to get done. If you think about, Engelbart was 100% concerned with saving the world. He was one of the most dedicated people I've ever met and thought about it for a long time. He was on task on all of the stuff that he did, and he had concluded that what you have to do is boost the collective IQ of groups of people working together in order to solve world problems. And that's what those designs, this is a loftier set of ideas than you'll find from any manufacturer today, any vendor. They just don't think that way, and you can tell. So that sounds dismal. On the other hand, you're at the right place for doing stuff, because a university is kind of a bastion. It's supposed to be a bastion against the hordes coming in to sack Rome. Right? So you're at a place here. The problem with universities is they can't get their act together as far as these larger groups things. And part of it has to do with the degree process, where they especially in technology, they wrongly try to get people to do individual PhDs. Whereas what you really want, what a PhD really means, is a person who does world-class work. And if they do that in a 10-person group, any advisor worth their salt will say, this is a PhD. We'll dub them PhD. And their thesis might have 10 names on it. Doesn't matter. Because if the advisor knows what they're doing, they know what the students are doing. And you have to realize that the PhD is saying, it's more like getting an MD. It's saying this person is qualified to be considered a world-class intellectual leader in their field. That's what it should mean. And to do the PhD, they have been an important part of edge-of-the-art research. So if universities could do, and I personally, every time I talk to a university president, I say, look, you guys are missing the century that we're living in right now. Universities have a unique position to actually help things out much, much more than they are right now, just because they're not supposed to be businesses. And they don't have to show a profit. And with the government being hung up the way it is, trying to get university funds involved in this stuff could be a tremendous difference compared to the way things are now. Yeah, I've talked to the, University of California has 4 or 5 universities in the top 10 in computing. And I pointed out to them that this is 4 or 5 in the top 10 in computing, and you guys are letting the regents tell you what tenure is? Are you kidding? Just take it over. It's not up to the regents what tenure is. They don't know anything about computing. Define what tenure means and define it differently than paper counting. Period. So part of the problem is faculties are more comfortable than they probably should be. Yes, sir.
Very last one.
Well, if you think about, say, these kind of paradigm-shifting periods in the context of 20th century capitalism. So you had Bell Labs, a lot of paradigm-shifting, deep research, deep thinkers, in the context of a company that had day-to-day business, you know, the telephone.
Yeah, of course it was a monopoly.
And it was a monopoly. And yet, so that incredible innovation happened in the context of a large capitalist entity.
Yeah, I don't think that's a good one. Precisely because I would believe that argument if it had sustained after the divestiture, but it didn't. It collapsed as soon as the baby bells went away.
But here's the point I was trying to make. You and your colleagues were kind of an inflection point to me where you were functioning within the context of, well, eventually of Xerox. There were precedents, but it came together in Xerox. Incredibly innovative. But then it became the classic textbook example of clueless management, business management. They didn't know what they had. They blew it off. It was
let me just
totally different from Bell Labs.
Let me put a little more context on it. So one of the myths about Xerox is that they failed to profit from PARC. In fact, they made their entire investment at PARC over by about a factor of 210. So if you work that out in return on investment, that is astounding. They made it from only one of the 8 things we did, which was the laser printer. That was the one thing they understood, but they paid for PARC hundreds of times over, all of PARC, not just the computing part of PARC.
But when you think of the large companies that followed, well, Microsoft and Apple, there's basically no innovation. They're just redeploying all the stuff. I mean, minor tweaks.
Yeah,
you know,
well,
but not major innovations like Bell Labs and Xerox. And then you think of the successor companies to those, Google, Facebook, and it's even more extreme.
Yeah. Even
less innovative. They're just rehashing a paradigm that you and your colleagues invented 56.
Well, I didn't invent it. I inherited it, and I was taught it as a graduate student. And
at Utah.
Yeah.
So it seems like something.
So Xerox here is a red herring because of this agreement Taylor got with Xerox, and the fact that the PARC people and the ARPA people considered PARC as just ARPA project number 17.
Right.
The reason PARC was set up at all was because of the Mansfield Amendment throttling the funding to the DoD for ARPA.
So is the secret to creating a context in which you have real fundamental innovation that you either need total government control or monopolies?
No.
Well, Apple is kind of a monopoly. I mean, these are Apple, Microsoft, they're sort of monopoly, but they've never done anything really fundamentally innovative.
Well, I think the capitalism. First, I think I would leave Bell Labs out, just because IBM is a much more interesting example, because it was a virtual monopoly, also, and back in the '60s when $1 billion was a lot of money, they spent $2.5 billion a year on R&D, of which 4 out of 5 working prototypes never went to market. So they had enormous resources. Their problem was they thought of their R&D as a hedge. And I think the most important thing is, if you compare, for instance, Friedman's notion of capitalism with Peter Drucker's. Friedman's idea, which is in vogue today, is capitalism in the United States is entirely at the service of the stockholders. You're trying to increase shareholder value, and that is it. Drucker said, no, that is a really bad way to think about it. Capitalism in America should be entirely at the service of the customers. That is what you should look at. But today, yes, just one more line. But today, the capitalism has to be at the service of the planet. It doesn't matter. Anything smaller than that is completely below that what is actually needed thing. It doesn't matter what you do with capitalism unless it's the blue line there is at the service of the entire planet, because that's what the system's nature of today is. And this is different than the system's nature of 100 years ago. It just is. And you basically have to go with what actually is.
Thank you for a long day and a great discussion.
And a long talk.
Please get home safely. Thanks for joining us.
Thank you.
Thank you so much. You're welcome.